This was the 2012 problem, number 3. It was the first one on your test. I'm going to go through this one fairly quickly because I went through most of this one in class, but just a quick review. We are graphing, we're graphing F, but all of the questions here are about G, G prime, G double prime, and again G, and then G. So although this is the graph of F, you really need to focus on the function G. And so when you interpret this right here, what this is telling you is that the function G is accumulating the signed area from 1 to x of the function f. So when I'm being asked to calculate G of 2, I simply want to calculate the signed area from 1 to 2 of f of t dt, which basically means I want from 1 to 2 the area of this, but it's signed area. So some of you didn't do negative. That was a triangle. You can work, I'm not going to do the arithmetic on these. That would be negative 1/4, not positive 1/4. Likewise, for G of negative 2, I would have, just substituting negative 2 in for x, from 1 to negative 2 of f of t. But we want to look at, again, we've been saying when we integrate it, it's easiest to think of it from left to right. And when we do that, we have to take the opposite. All right, so really what I'm doing is I'm going from negative 2 to 1, which would take me along this triangle and then this semicircle. When you find the areas of those, be very careful with your signs. This one's positive, this one's negative, but when I'm done, I need to take the opposite of that. So I'll let you do the arithmetic on that one. When you're all done for that, you should get a negative 3/2, which makes sense because the area of this one is 3/2, but I'm taking the opposite. And then I would get a plus pi over 2. And again, it's because the area of this is negative, but I'm taking the opposite. For part B, now it says to calculate G prime. Well, when we're doing G prime, all right, that's the second fundamental theorem of calculus that says when I take the derivative of the integral with an upper boundary of x, I can simply say that that is f of x, and we've derived that many times. So G prime of negative 3 is really just f of negative 3. So all I'm being asked to do is go to negative 3, and on the value of f there is simply 2. Likewise, G double prime of negative 3 would then be f prime at negative 3. So I'm really being asked to find the slope of the tangent line when x is negative 3. So really what I'm being asked to find is the slope of this line. And when you use your slope formula on that, you end up getting a 1. Next, there's always questions about tangents and maxes and mins and inflection points that go with these. The key to remember is what you have a graph of. So I'm going to go back up here and remember this is the graph of f, which is really right here, okay, G prime. So it's important to note that. Now it says find the x-coordinate, so I only need the x-coordinate where G has a horizontal tangent line. Well, horizontal tangent lines on an original function occur where the derivative is equal to 0, or consequently where G prime is equal to 0. Where does that occur? Well, G prime is equal to 0 right here and right here. Now you need to justify that. So for part C, you would say at x equals 1 and x equals negative 1, but you have to justify why you picked those. So the best thing would be, just a nice succinct answer would be to say because G prime of x equals 0 here. And some of you put because f of x equals 0, and again they're equivalent functions, so that would suffice also, but you don't need to write a whole lot for that. Then it says to decide whether there's a minimum or a maximum there. So let's look at x equals 1 first. Remember, this is the graph of the derivative, and what this is saying is your derivative is negative here, and then it's still negative. So what that means is I had neither a max nor a min over there at x equals 1. So you'd say at x equals 1, neither a max or a min, but you have to say why. And it can be as simple as because the derivative, which is G prime, or you could say f, does not change sign. Or some of you said the function's decreasing and continues to decrease, that's fine. Some of you said g prime was negative and continued to be negative, which is also perfectly acceptable. And at x equals -1, let's analyze what happens. Again, this is a graph of g prime, and it's going from above the x-axis to below the x-axis, which means the derivative was positive, and then it was negative, which means the function was increasing, and then it was decreasing, which indicates that that would be a maximum. There is a relative max, okay, because, and again, you always need to try to justify it with as few good words as possible. So why is there a relative max there? And you would say because g prime changed from positive to negative. And you'd write those words out. Or you could say, because g, the original function, must have been increasing and then decreasing. Alright, those are equivalent statements. Alright, and then for part D, we're looking for inflection points. Now, algebraically, when we're looking for inflection points, we do set the second derivative equal to 0, and then we do test to the left and test to the right. But graphically, the best explanation is just to look where the derivative changes from increasing to decreasing. Or you could say where the second derivative would change signs. Well, now, this is the graph of the first derivative. So right here, the second derivative would have been positive, and then it would have been negative, because it's the slope of the slopes. And they're negative, 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 negative. And then again, I have slopes becoming positive, correct? And then again, negative. So I actually have 1, 2, 3 places where the slope of g prime changes signs, which would be g double prime. Or you could say where g prime goes from increasing to decreasing. Those are equivalent statements. So the best way to write this would just be to say at x equals -2, 0, and 1. And I can wrap those all up with the same reason. And I can just say one of two things. I like this one. I like to say because g double prime changes sign here. And even if you wanted to be more specific, you could say because it goes from positive to negative, indicating a change in concavity from concave up to concave down. I mean, you could be really, really specific, but this will suffice. The equivalent statement would be because g prime changes, but not from positive to negative, it would be from increasing to decreasing. Either one. I like this one. Some of you were using because g double prime equals 0 or does not exist here. That's a more algebraic reasoning when you're given the function and you're given it in terms of an algebraic expression and you're looking. Then you say, well, where is the function's second derivative equal to 0? Where is it also undefined? Because you'll notice right here, this is undefined. And then we do run a sign check on it with a sign line because we have to make sure there's a change. Because, for example, right here, I would get a vertical tangent, which would mean it's undefined, but I have no change. So again, graphically, I think the best explanation for the second derivative is just because the second derivative changes sign. Okay, it goes from positive to negative. Or g prime goes from increasing to decreasing. Either one of those would be good. So that's that one. Let's see, I've got 6 minutes, so I'm going to start the next one, and I'll probably have to do these in 2 videos. So that wasn't the next one, was it? No, that was the third one. I'm going to go back. Where do I have the other one here? 1, 2, I wonder if I have it on this page. Yeah, here is the next one that you had on your test. I had them a little out of order here. And again, I think this was the 2009 one. But again, this is the graph of the derivative. Okay, and I'm being asked questions about, let's see, f, the original function, which means I'm going to be doing some integration. I'm being asked about inflection points, so I'm going to have to be doing the derivative of the derivative, or kind of looking at the slope of the derivative graph. So on the first question for part A, again, I'm looking for those inflection points. I want to know where the derivative graph goes from decreasing to increasing or increasing to decreasing, or equivalently where f double prime changes sign. So let's look at where this happens. Again, this is the graph of the derivative. So when I'm looking at this derivative of the derivative, it's negative, it's negative, it's negative, 0 here, positive, positive, positive. So I would say at x equals negative 2 for sure. And right here I've also got to change x equals 0. And again, the best reason for this, I wouldn't say because the second derivative is 0 or undefined. That's an algebraic explanation. Graphically, I would just say since f double prime changes sign. Again, f double prime would be the slope here. It'd be negative and then positive. Or equivalently, you could say because f prime, this graph here goes from decreasing graph to increasing to decreasing. There's a change in that. All right? So that's part A. Part B. Okay, and then this one's a little trickier because you need to know your fundamental theorem of calculus and how it works with these graphs. So really what I'm looking for is I'm looking for f of 4. Right? And when I'm giving the graph of a derivative, what that's telling me is I'm going to have to integrate. So what I would do is I'd use my fundamental theorem of calculus and say, well, I'm looking at f of 4, which I can get at by integrating from 0 to 4 of the derivative graph. Now I can even put f of x dx. That's perfectly fine. And when I do my fundamental theorem of calculus, what that does is it says take the antiderivative, which would be f itself. The derivative of f is f prime, so that's kind of nice. Remember, these two functions, kind of, you can think of them as undoing each other, like squaring and square rooting. So I do get f at the top boundary minus f at the lower boundary. Well, this is the one I'm trying to get at. I want to know what is f of 4. Now, in a real life context, what this is kind of telling me is that to figure out what I have at the end of, like if this was time, at the end of, say, 4 hours, when I'm given a rate of change, what it's saying is I need to know how much it started at so that I can do this. Okay, I can say that f of 4 is really equal to, if I add this to both sides, how much did I start at plus how much did it change. That's kind of real world context what this means. Now what I need to go do here is I need to go see how I can get at this with my graph and my statement right here. Now since I chose, I'm actually doing this one first, I should have probably done that one first. It doesn't really matter, but I am doing from 0 to 4, I can't get at that with geometry because you can see I've got like a curved thing here. I have no idea how to get the area under that curve. Geometry is the best if you can use it. But what they're testing here is that you know how to find the antiderivative and how to integrate the transcendental function right there. So let's go do that. What I have here is f of 0, which they gave me. This is why they gave it to me. That was kind of a hint that you were going to need to use it. And then I'm going to have to integrate from 0 to 4 what the derivative is in that piece of the graph, which would be 5e to the negative x over 3 minus 3. And some of you have been leaving your bookend of the dx off of there, which bugs me, but I don't think it's that big a deal. All right, so now what I'm testing here is, do you know how to integrate that? What you might want to do, you know, there's several options here. You might want to just take that 5, let it sit out front. Okay? You know that subtraction can be split up. But again, I'm taking this on my own, maybe a simpler route for some of you who got stuck with the integrating. But you'd go from 0 to 4, this constant can front, e to the negative x over 3, then minus, right? It would be the integration of 3x, because that's the antiderivative, and that one's going from 0 to 4, and you could immediately replace that with a 12 if you would like. What that does is it kind of gives you a little simpler approach to this, so it's not quite so ugly, I think. So, you know, that's up to you if you want to do it like that, which really means you just need to work on integrating and finding the antiderivative here.